Welcome again to another episode of Sir J Maths, where we'll be looking at a topic called bearings. Now, this is a significant topic in mathematics and also in CXC. A lot of students are fearful of this topic, but you don't need to be fearful. Watching this video, you'll get a lot of insights into how to solve CXC bearings questions. So please look. Now what exactly are bearings? Now we have looked at angles before, and an angle is simply a rotation about a point. So if we have a point like this, and let us say we have a line segment called A, B, then an angle is simply a rotation about this point, where this line segment can be shifted basically or rotated about this point until say B comes somewhere here. So now B is now in a new position, but the position of the center of the rotation does not change. So what happens here is that the size of the rotation or the angular measurement right here would actually get the angle. So it's the degree of turn or the amount of turn that actually determines the size of the angle that is formed. Now, bearings are special types of angles. Now, these angles are measured from north, but in a clockwise direction. So, when we speak about clockwise direction, just look at the hands of a clock. So if that is 12, watch this. So if we draw a circle or make a representation of a circle, then let us say the hour hand is here. So you have 1, 2, say 3. Now the hands of a clock, whether it is the hour hand, the minute hand, or the second hand, tends to move in that rotation. That is a clockwise rotation. So they tend to move in that direction. Now, the hands of a clock would not move counterclockwise or anti-clockwise. So bearings are special angles measured from north. Now up here is where we call north. So on a plane paper, on a plane, basically north is somewhere above any particular point. Now a plane is simply a flat surface. Okay? So right here, if we put this point here, then the direction directly above this point on a plane paper or on a plane sheet is considered to be north. Now, the thing about bearings is that, yes, they are special angles. They are measured from north in a clockwise direction, but north is taken to start from 0 degrees. Now, it is of note that in the unit circle, angles are measured in a clockwise direction normally, where right here is 0 degrees. Now, angles that are positive tend to go in a anti-clockwise direction in the unit circle, anti-clockwise. So this right here would have been positive 90 degrees if we are taking that direction. But if we are taking it this direction, clockwise, then that would have been negative 90 degrees. So anti or clockwise angles in the unit circle tend to be negative, while anti-clockwise tend to be positive. But dealing with bearings, up here is 0 degrees, and as I said, these are special types of angles. So we are going to travel clockwise, but then for these types of angles, they are positive. So don't mix up bearings with the angles in the unit circle right here. Now, if we divide the circle into 4 quadrants, then we know that 1 revolution equals 360 degrees. And so right here, we would divide this, say, the unit circle, or as a circle, into 4 quadrants. So between north and east, right here would have been 90 degrees. So hence, the direction from north, so east is 90 degrees, or is on a bearing of 90 degrees from north in a clockwise direction. South is 180 degrees, where angles on a straight line would measure 180 degrees. West now has a bearing of 270 degrees, because coming right here, we'll have north, we'll have south, we'll have east, we'll have west right here. So again, 0 degrees, and if you notice right here, the digits are really 3 digits. So bearings, what makes them special as well is that we tend to use 3 digits at all times. So east of this point basically is 90 degrees, but we don't write 90, we write 090, which is 90 degrees. So south right here is 180 degrees. And west is another 90. 90 plus 90 gives us 180. 180 plus 90 would give us 270 degrees. So west right here is 270 degrees. And if you notice, these are what you call the cardinal directions: the north, the south, the east, and the west. However, if the direction directly between north and east is northeast. The direction exactly between west and south is actually southwest. The direction between north and west, exactly between north and west, is northwest. And the direction between south and east is actually southeast. And so right here we tend to use arrows, because arrows tend to denote direction. For it to be a direction, you must have the arrows. Okay. Now, let us say we want to represent certain bearings, sketch bearings. That is, we are going to represent a bearing without it being, or without them being exact. So it's just a sketch, because CXC most times asks you for a sketch. Okay, we want to sketch a bearing of 60 degrees. Now this is an instrument called a protractor. Now this protractor can measure essentially a maximum of 180 degrees. Now, but we are not going to sketch this exact, so we are not going to use this to measure our 60 degrees. But we could at first and then do an estimate. So the first thing that you need to do is a bearing of 60 degrees would be taken with respect to a particular point. So what you do, you put your point. The next thing that you do is to draw your north line, which is a vertical line, or we could call it the north-south line, and we need to establish north. And then we could also do a little line, basically our east-west line, and right here. But on the questions, they usually ask just to denote north. So right here is north. So right here is your point. Now, if we were going to measure 60 degrees exactly, what we would do is to put our protractor with our inside baseline right here, with the center piece right here to coincide with the point, and ensure that our line, our inside baseline, runs exactly on the north-south line, covering it. And then remember, we are going to measure from north in a clockwise direction. So that is 0 clockwise. We'd go 10, 20, 30, 40, 50. 60 degrees would come exactly right here, and we put our point right there, and then we take up our protractor or our ruler, and we would measure this coming right here, and this would be our 60 degrees, and then we use an arc to represent our angle. So right here we write 60 degrees, but remember, we have to put the 0 in front to show that it is bearings, which is a special angle. So we have our 0, 60 degrees. So remember, it is not 60 degrees really, it's 60 degrees, but we put a 0 because it must have 3 digits. Now we could have sketched our 60 degrees without using our protractor. So first you draw your north, south, east-west line, and then you know that east has a bearing of 90 degrees. So okay, between here and here, 3 sets of 30 would give us 90. So it's like divide it into 3 equal portions. Somewhere here would have been our 60 degrees. So right here is an estimate of, say, your 60 degrees. And you would put that, and then you would have your north. So let us say we want a bearing now of, say, 130 degrees. So again, we put a point, we draw our north, south, east, west line through the point. So this is a point, this is north, then you have your like a east-west line. So your east-west line, and you don't have to put the arrows, just put the arrow for the north here, and then 130 degrees. Now remember, right here is 90 degrees. So clearly 130 degrees is greater than 90 degrees. Down here is south, which is on a bearing of 180 degrees. So it means that 130 degrees would come between 90 and our 180 degrees. Now if we check over here, halfway between east and south is actually southeast. So halfway right here would have been 135 degrees. And so 130 degrees is a little bit less than the 135 degrees. So right here is a bearing of 135 degrees. And notice I basically take an arc or represent an arc and show an arrow. That is, I'm traveling from north in a clockwise direction until I reach right here. Now we could break it down. We know that right here is a right angle measuring 90 degrees. Now if we're not taking it as a bearing but just as an angle, then we don't put our zero, we don't put a zero before. So if you are just looking at it from an angle perspective, that is 90 degrees, and right here would have been, if I take 90 from 135, so it should have been 130, 130 degrees, I would actually get 40 degrees. And so right here is 40 degrees. Notice there is no zero because it is not a bearing. It is just an angle. Now, let us say we are going to sketch a bearing of 240 degrees. So again, you must have a point at which you are going to take the bearing from, or bearing off, and then you draw your north-south, east-west line with your ruler. So you have your north, you can do a little thing like that. So this would have been your east-west. This is south, this is north, 240 degrees. Now, we already know that south has a bearing of 180 degrees. So what we want is a bearing of 240 degrees. Now, west is on a bearing of 270. So we would take from north, come somewhere here, come right around. However, we would not come all the way up to here because a bearing right up to here would have been 270 degrees. But what we want is a bearing of 240. So it simply means that 240 must come between the 180 and the 270. But as a sketch, you need an idea. How far? Now, if we go right back here, southwest, which is the cardinal direction between south and west, is on a bearing of 225 degrees. And that is halfway between south and west. So it simply means that our 240 degrees is actually 15 degrees away from our southwest direction. So you could use your ruler and you do something like that. And this is an estimate. And here you would have a bearing of 240 degrees. Now, if we were to break down this, angles on a straight line measure 180. So this would have been 180 degrees. And if we take 180 from 240 degrees, right here would have been 60 degrees. Now notice I wouldn't put a 0 before the 60 because this is just a regular angle and not a bearing. because it is just the angle inside here, which is not an angle, which is taken from north. So please make note of that. Now, let us say we also want a bearing of 310 degrees. Again, draw your north, south, east, west line. So you put your point here. So you draw your north, south, east, west cardinal direction here. So 310 degrees. So what we know is that west is always on a bearing of 270. So somewhere here is 270. But what we want is 310. So 310 degrees is more than the 270. If we complete one complete turn or one full turn from north straight around back to north, then we'll have completed 360 degrees, which is actually one revolution. So 310 degrees is 50 degrees away from our north, from the west direction right here. Now, northwest, if we come right up here, northwest is 315 degrees. So, northwest is immediately between, or actually exactly between north and west. So 310 degrees is very close to northwest right here. So we could estimate it and put it somewhere here. So right here is our bearing of 310 degrees. Now it is of note that, okay, right here is 180 degrees, that is angles on a straight line. Right here is 90 degrees, which is a right angle. Between south and west is a right angle. So if we want to find this piece, what we could do, 180 plus 90 is 270. 270 from 310 is 40 degrees. So right here would have been 40 degrees. Notice we wouldn't put a 0 in front because it is not a bearing, but just an angle. Before we do any bearings question, there are a few things that you must know. You must be cognizant of. Bearings questions usually take in different types of angles. Now, one such angle is what we call Z angles. So if we have Z in this fashion, and with Z angles, it is of note that these two lines or line segments must be parallel, and right here would be a transversal. So the angle inside here and the angle here are always equal once you have a Z letter or a Z shape. Now, the Z can always be orientated in different directions. So right here, we could have our Z looking like this. Sideways Z, it doesn't matter. Upside down Z, something like this. Right? As long as these two lines are parallel, then we have a Z. So this angle and this angle would be equal. Now it is of note that these two lines must show that they are parallel. So you have to have the arrows. And remember that this is a transversal, this is a transversal, this is a transversal. Now you need to also look out for U angles. Now U angles basically, as the term suggests, look like a U. So these two lines are parallel and this is a transversal. Now with U angles, co-interior angles, these two angles are together, they are inside together, they are interior angles working together, so we refer to them as co-interior angles. And the relationship between these two angles is that they are supplementary. That means both of them add to give us 180 degrees. So whenever you are looking or whenever you are dealing with bearings questions, you will meet upon co-interior angles or U angles and also Z angles. Now, you also will meet upon at sometimes right angles, and we know that that is a right angle. Now, let us do a CXC question. Okay, now this CXC question. An oil tanker leaves town X and travels on a bearing of 50 degrees to town Z 50 kilometers away. Now, there is no need to read through all the question first. What you can do is to begin by doing basically a sketch. Now, the sketch usually takes in a triangular course. So whenever CXC gives you a question, a bearings question, generally speaking, you are expected to have a triangular course. So an oil tanker leaves town X. So you must have a starting point. So your starting point is, let us say we put the point here. Now, it leaves town X, so it means that the starting point is at X. So you put the point, you label the point here X. It travels on a bearing of 50 degrees to town Z. Now, a bearing of 50 degrees, remember, I would have shown you how to estimate a bearing. So the first thing that we'll do is to draw our north line. So we'll have the direction here north, you put N, and then you would have your east-west line like that. Remember, east has a bearing of 90 degrees. So 50 degrees is a little bit more than a halfway between north and east. So what we can do here is to draw something like this, and then the oil tanker traveled from X to Z. So up here is Z. On a bearing of 50 degrees, we put in our 50 degrees bearing, and then the distance it travels is 50 kilometers. So right here we put 50 kilometers. Now the oil tanker is at Z. Now I want to tell you this, and watch this. If the tanker travels in this direction, no matter the number of miles, 1 million miles away, then the direction will be the same. But the question now says that the tanker then travels to town Y 75 kilometers away on a bearing of 120 degrees. So this is suggesting that the direction of the oil tanker actually changes. So it changes when it reaches Z. Now, students, anytime you are going to have a change of direction, you must draw up a new north line. So right here, we are going to draw a new north line. Now, let me fix up this a little bit so it shows, kind of show that they are parallel. So here is my north line. Now remember, over here was another north line. So right here, I would put my east-west line right here. Now, the tanker traveled 75 kilometers on a bearing of 120. So 120 degrees, remember, east is 90, south is 180. 120 degrees is somewhere around here. So we have somewhere around here is our 120 degrees. So right here we have 120 degrees. And then we know that the distance of Y from Z is 75 kilometers. So you put that in. Now it says, draw a carefully labeled diagram of the tanker's journey, clearly showing the north line. So we would have illustrated the journey already. Now calculate the distance of Y from X. So Y from X, what we need to do is to connect X to Y right here. So you use your ruler and you do that. But we need to calculate it correct to 3 significant figures. So this is what we want to find. So this is our sketch diagram. So right here we have our bearing sketch diagram. Now, students, listen. You cannot do a bearings question without sketching the diagram. So you need the diagram for you to do the bearings question, especially when it is this technical. So now we are going to calculate the distance of y from x, so which is the distance xy. Now here is our sketch diagram. It is best for you to draw another triangle looking the same but without the bearings. So simply you do like this, and if you notice I actually represented the distance yz a little bit longer than the distance xz, even though it is not drawn to scale, because this is 50 kilometers and this is 75 kilometers. So what we actually did, we made this come down a little bit longer than that one. So right here we now have our triangle looking like the one in the sketch. So we have x is right here, z is right here, and y is right here. Now let us put in what we know. We know that this is 50 kilometers. We know that this is 75 kilometers. Now what is it that we know so far? Now we know two sides of the triangle. Now if you remember something, if you go back to the sine rule and the cos rule, if you remember that if we have two sides, so this is like side over here. So if we have an angle inside here, so this would be the angle, so we'd have side angle side, then we can basically use the cos rule to find the length of xy. So side angle side, SAS. So what we do is, alright, we set out to find this angle inside here. Now how do we find this angle inside here? We go back up to the sketch diagram. So the sketch diagram, the angle would be right here. Alright. Now let us find the angle inside here. Alright. We know that angles on a straight line measure 180 degrees. So this would be 180 degrees. This is a straight angle, 180 degrees. So this is a north line. So angles on a straight line on the north line would measure 180 degrees. So right here we already know that this piece is 120. So clearly when we take 120 from 180 degrees, this piece here is 60 degrees. Alright, so we know that this angle is 60. What we now need to find is this piece right here. Now let us get back to the Z angles that I was showing you. So right here, this is a north line, this is a north line. What's the relationship between these two north lines? They are parallel. So these two north lines are parallel. So clearly this is a transversal. So right here is a transversal. Now what did we say? That this angle equal to this angle. These are the two Z angles. These are Z angles and are alternate angles. So if this is 50 degrees, then this is also 50 degrees. So we put 50 degrees right here. So therefore the total angle at Z is 50 plus 60, which gives us a 110 degrees. So right here we drop in 110 degrees. So good. Now we have side angle side. Now when you have side angle side, here we have three elements. We want to find xy, which is little z. So little z, we don't know. Which rule are we going to use? Two sides and an included angle. To find a third side, we use cos rule. So we can write using the cosine rule. What are we finding? Little z. So it's little z squared equals, now if this is angle y, over here is little y, angle x over here is little x. So based on what we did in the cos rule, it is the sum of the squares of these two sides, which is y squared plus x squared minus 2 times the product of these two sides, yx, times the cosine of the angle that is opposite to the side that we want to find, which is angle Z. So then little z squared equals y, which is 50 kilometers, but I'm going to leave out the unit for the time being. So I have 50 squared plus x, which is 75 squared, minus, put that in bracket, 2 times 50 times 75 times the cos of 110 degrees. So little z squared equal 50 squared is 2,500 plus 75 squared. This number has to end with 25 based on what I taught you before. And I simply say 7 times 8 is 56. So that's 5,625 minus, now 2 times 50 is 100. 100 times 75 is 7,500 times the cos of 110 degrees. 110 degrees is in the second quadrant, so it is negative. So when I find the cos of 110, I'm going to get negative 0.342, correct to 3 decimal places. Get our calculator and we add 2,500 plus 5,625. We get 8,125. So we write little z squared equal 8,125 minus, now I multiply 7,500 times negative 0.342, and I am going to get negative 2,565. Now right here I know that I am going to add when I remove the bracket, because the negative outside will change the sign on the inside. So I simply add 8,125 to 2,565, and I get 10,690. Now this is saying z squared equal 10,690. What number, which when multiplied by itself, give us 10,690? So what we need to do is really to find the square root of z squared in order to find what z is. And then we also find now the principal square root, which is a positive square root of 10,690. So we don't really put positive or negative here because we are dealing with length, and so the negative root is not possible. So right here we now find the square root of 10,690, and we are going to get 103. So now it's z now equals, but the question says give it correct to 3 significant figures. So we have 103.392. But 3 significant figures, we begin from the left, the first non-zero digit. So this is significant. This is also significant. Now zeros on their own are not significant. So if I have 100, we only have one significant figure here being 1. These two are not significant. For a 0 to be significant, the 0 has to come between 2 digits from 1 to 9. So this 0 comes between 1 and 3. Therefore, this 0 is significant. Now, to express it to 3 significant figures, here we already have 3 significant figures, 1, 0, and 3. But you need to look at the 4th digit, which is 3. It is in the 10th position. Now, since it is less than 5, or 5/10, it is not sufficient to change the previous digit by 1. So it is 103, that is little z, equals 103 kilometers. Now, we had set out to find xy, so we can say, therefore, xy equals 103 kilometers. Now, it's the same. Now, part C of the question. Calculate the bearing of x from y, giving your answer to the nearest degree. Now, calculate the bearing of x from y. Now, let us go to the diagram here. Now, right here, we got that the bearing of z from x is 50 degrees, or the bearing of x to z is 50 degrees. Now, a bearing of x to z, watch this, x to z is 50 degrees. That is the bearing. But we could also say the bearing of z from x. So watch this, z from x, our starting point is at the letter on the right hand side. So anytime you have the word from, and you are going to take the bearing, so it's first point from second point. Now the starting point is always at the letter on the right hand side. And so if we come here, calculate the bearing of x from y, where is our starting point? Our starting point is at y. So the bearing would actually begin at y, and then we go to x. So what we are going to do is we want to get the bearing of x from y. So clearly we need to take the put a north line here at y, because anytime you are going to measure bearing, you have to set up a north line. So right here we set up our north line and we put n. It is very important that we put n. And what we can also do is to put a little east-west line right here. Okay? So remember, right here is y. Now the bearing is x from y, which is y going to x. So we use an arc starting from north, clockwise direction, until we go towards that line going to x. Now we don't have to go all the way over to x, because what we want is the direction. If it is a distance, we go to x, but the direction, as long as we drop anywhere on this line, then that is the direction or the bearing of y to x. So we put that little arrow right here. Now when we look at this, all of this is the bearing that we want. Now let us backtrack a bit. We know that when we complete one revolution, then one revolution, that is starting from a point, and you rotate about that point until you go right around and end up right back at the point, then you would have completed 360 degrees. So all of this coming right back here would have been 360. All right, so just remember that. But if you remember, we looked at U angles. Now U angles look like this. As long as these two lines are parallel, then these are two co-interior angles, and then they are supplementary. But the U can go in any direction, can be orientated. And so this is also a U. So let us check if we have a U. Now right here we have our north line. We also have a north line. Now if we extend this, then here we are seeing that U. So here we have a U shape. So with the U shape right here, watch this, with the U shape right here, as long as these two lines are parallel, which is these two north lines are parallel, then this is a U. So if this is 120 degrees, then clearly this is the other interior angle, or these two angles are co-interior. That means they are supplementary and they add to give us 180. So what we need to do is to take 120 from 180. So this angle right here is going to be 60 degrees. So we drop in 60 degrees here. Now we didn't have to use the co-interior angle or the U angle. We could have also used Z angle, because right here, watch this, here is that Z, because this is a north line, this is a north line, this is a transversal. So right here, if this is 60 degrees, then this piece is also 60 degrees. And notice we never have 0, 6, 0, because it is not a bearing. So right here is 60 degrees. All right. So remember what we said. If this is one revolution, then all of this would be 360 degrees. Now when we come right here, this is just the angle we want right here. So this is the angle we want right here. Now if we can find somehow this angle inside here, if we can find this angle inside here, we could take it from say 300 degrees No, why 300 degrees? All right. If this is 60 degrees and everything from here come right around is 360, then what is left? Everything that is left would have been 300 degrees. Because 60 from 360, that is a one revolution or angle at a point, is 360 degrees. So if we take 60 from 360, clearly we are going to get 300 degrees. So all right. So we agree that this angle, this full angle here, our bearing must be 300 degrees. So if we can find this angle inside here, what we could do is to take this angle from the 300 degrees and it would give us the bearing from here to here. Because what we want is a complete bearing right up to here. But we know that from here to here, the bearing is 300 degrees. So if we can find this angle inside, we can take it from the 300. So we set out to do that. No, we set out to do that. So let us write a plan. So what is it that we want to find? We want to find this angle right here, which is angle Y. So as a matter of fact, we can go about drawing back a new triangle right here. Let me use this color. So we have Z, we have Y, we have X here, we have Y right here. So this is the angle that we want. So what we want is clearly angle Y. Over here, little y equals 50 kilometers. Over here, this is little x, which equals to 75 kilometers. And right here, we want this angle here, which is angle Y. We already know this angle, which is 110 degrees. So what we want here is the angle. Now we actually worked out XY, and we worked XY 103 kilometers. But remember that the 103 kilometers was actually a rounded off value. Now, if we want to find angle Y, if you go back to the videos, the sine rule and the cos rule, yes, we could use a cos rule because we have side, side, side. 3 elements, 3 sides, so we could always use the cos rule to find an angle. But what I am going to do is to use the sine rule instead. And so we write down the information that we want. We want angle Y. So big Y is what we want. The big angle denotes, or the big letter denotes the angle. So big Y I don't know. If I want the angle, I have to know the side opposite to the angle, which is a little y. So little y here equals 50 kilometers. Now, here I know side x, but I don't know angle x. So if I am going to use a sine rule, I cannot use y over sine y equals x over sine x. Because if you remember, to use a sine rule, 2 relationships, but I must know 3 elements and one side that I don't know, and I would set out to find that side. So because I know angle z, big Z here equals 110 degrees, I would have to know little z, and little z here equals 103 kilometers. So I'm going to use the sine rule. So remember the sine rule, I can say little y over sine of big Y equal little z over sine of big Z. So here I write y over sine of big Y equal little z over sine of big Z. So little y is 50 kilometers over sine of big Y, which I don't know, equal little z, which is 103 kilometers, over the sine of big Z, which is 110 degrees. Now, since I want sine Y, I can cross multiply here. So I have 103 kilometers times the sine Y equals 50 kilometers times the sine of 110 degrees. But I want sine Y, it is being multiplied to 103 kilometers. So I divide here by 103 kilometers. all of this gone. I must also do it to the right hand side to maintain balance. So I divide this by 103 kilometers. Right? So what I have is sine y equals, and I get my calculator, and I find the sine of 110 degrees, which is in the second quadrant. 110 is in the second quadrant, but the sine is positive, unlike cosine. So it's sine of 110 equal, we have 0.9396. Now watch this. 0.93969 whatever. But what if we want to round it off to 3dp, that is the sine of 110, 939, but the 6 would change the 9 to 10, 10 to change the 3 to 4, so we'll have 0.940. So we write 0.940. That is 50 kilometers times 0.940, as in rounding off the sine 110 to 3 decimal places, divided by 103 kilometers. So what we have here now is the 50 times 0.940, and we get 47. So it is 47 kilometers over 103 kilometers. Kilometer cancel kilometer. Now we divide the 47 by 103. 47 divided by 103, and that gives us 0.456. So what we have is that sine y equals 0.456, correct to 3 decimal places. Now, are we finished? This is sine of an angle. That's the angle we want to find, whose ratio is 0.456. So what we want is y. So y, though, is the sine inverse. So to access the angle, we need to press sine inverse of the ratio 0.456. So y equals, I will press shift sine inverse 0.456, and that equals to 27.1 degrees. But if we go back to the question says give it correct to the nearest degree. So to the nearest degree, we are going to look at the units position, and the 10th position is not able to change the units position. So to the nearest degree, we don't have any decimal places. So therefore, angle y equals 27 degrees to the nearest degree. So this is angle y, which is 27 degrees. So remember, this is 27 degrees. So therefore, we are going to sum up now. The bearing of x from y equals, remember the plan, it is 300 degrees, because all of this we said is 300. So it is 300 degrees minus the 27 degrees, which will give us, when we subtract 327 from 300, we get something like 273 degrees. We would have found the bearing of x from y. Now we have come to the conclusion of another video on Sir J Maths channel, where we try to make maths easier, more simplified. Please tune in for another video, and I want to encourage you to tell people about this channel and also encourage them to subscribe. See you guys next time, and what you can do is also to like this video or like my videos, and remember, encourage them to subscribe. Thank you very much.